Hello, everyone. So, my name is Andrey Norkin, and I'm making this presentation in two different kind of roles. So, I am a research scientist at Netflix, and I'm also a co-chair of the Codec working group in the Alliance for Open Media. So, first of all, I would like to thank people who contributed to the slides. So the materials are based on from the materials of the contributors that you could see it, because that basically describes the AV2 video codec. So many people contributed and to the codec, and also to making the pictures and writing text about it and so on. So first of all, I think Yanis spoke about it a little bit, so I will be very brief. 2015, the Alliance for Open Media was established, and 2018, the AV1 was released, the first video codec from the Alliance, and in 2020, we started working on the next generation video codec. So in 5 years now, basically the codec working group has been working on this new generation codec, and basically a lot of tools have been brought to the it was based on AV1 model first, and then a lot of tools were added there, and some tools removed. So basically all the tools, they received rigorous scrutiny from the hardware implementers that also participate in the group. You can see the list of companies who contributed, and also some companies they do hardware review. Of course, some of the contributors, they also do hardware review because they are also manufacturers. So recent AV2 results, Ryan is going to speak about it in more details, but the latest anchor, AVM version 11, we get PSNR YUV BD rate, basically 28.6% savings compared to AV1. And in VMAV, this number is about 32.6%. That's on the random access, which is the most common, most efficient configuration that is typically used. Now to AV2 framework. So I will really try to be very brief describing the tools, because it's very difficult to fit all of this basically AV2 description into 20 minutes. So. But I'll try. So first of all, the video codec is basically a typical hybrid block-based model that has existed for at least like 35 years. However, many tools have received changes if you compare to AV1. So you see, like, for example, first there is a partitioning, then you, for blocks, you use Intra prediction or inter prediction, so prediction from other frames. The residual is transformed and quantized, and the quantized coefficients are entropy encoded, and you also have loop filters that basically improve the quality of the pictures before they are saved into the reconstruction. Reconstructed pictures are saved into the decoded picture buffer, where they can be used for prediction. So first, the partitioning. Compared to AV1, we now have larger block sizes, up to 256 by 256 for super blocks. In AV1, you could have these types of partitions. So each basically block could be partitioned this way. And the one with R is basically the subdivisions could be done recursively. So you can actually have a recursive split. Now in AV2, it has changed. So some of the partitions were removed, and some more partitions were added. And now, basically, all of them are recursive. So you can actually have recursion in any of these blocks, down to the smallest block size, if you really want. Transform block partitioning has changed as well compared to AV1, which is on the left-hand side. So in AV1, you could have like 2 levels of transform split. In AV2, it's only 1 level, and the partitions are different. So one tool is semi-decoupled partitioning. Typically in the codecs, or in many codecs, the chroma and luma partition trees are basically the same. In AV1, they're the same for the larger block sizes, but at a certain point, they can actually use different partitioning for luma and chroma, which is helpful on, for example, sometimes if chroma is very low pass, then you don't want to subdivide it as much. Intra prediction tools. Here is an example of multiple reference line selection. You can use up to one of the 4 lines on the top and to the left to predict the current block. And you use it, typically you use the same like directional Intra prediction as in many other codecs, but you can pick actually now the lines which you use for prediction. Another tool is adaptive intra-mode coding, and that's related to ranking the available modes and then also splitting them into the sets, and typically the most probable set is cheaper to signal, so it improves the bit rate. An interesting tool, Intra by prediction. In a typical directional prediction, you predict from one direction, but now you can actually, for some of the modes, like if the reference samples are available from 2 sides, you can actually do the prediction from the other side as well, and then you average the results with weighted based on the weights, where you basically get the higher weights for the prediction that is where the reference samples are closer. So it really makes the prediction more efficient. Another tool, data-driven intra-prediction. So in this case, you downsample the neighboring samples first, like the reference samples, and then you produce a 8x8 blocks of samples using pre-trained matrices. So you can choose one of which of the matrices is used. It's kind of a little bit similar maybe to the neural networks, but without the sigmoid function. And then you upscale this, the residual to the block size, and you can use that. Another type of prediction is chroma from Luma or MHCCP, which is a multi-hypothesis cross-component prediction. In both cases, basically, you try to predict your chroma based on the Luma. And for example, in the CFL chroma from Luma, you would use a linear model. There were some improvements, in particular, some of the model parameters compared to AV1, they can be derived implicitly, which again reduces the bit rate. A multi-hypothesis cross-component prediction, it uses a more complex model to do the prediction, but the idea is similar. Now I'm going to move to the inter-prediction tools. First of all, you need reference pictures, and in AV2 you can have up to 7 reference pictures, which are arranged in the list based on some factors such as the temporal distance from the current picture, the quantizer, the frame resolutions, and so on. So basically the benefits is that you would probably get the best frames for prediction closer to the beginning of the list, and then you use the unary code word, and so it's cheaper to signal than for the block to signal the frames which are likely to produce better quality. On the prediction modes, there are compound modes, which is basically the by prediction, and different types of compound modes. Like the easiest one, you use equal weights from the blocks and you average the block. You also have a weighted prediction, where you can actually signal the weights for 2 frames, so 1 frame can have a higher weight. More compound modes, there is an implicit wedge mask, for example, and that's in the case when one of the blocks, for example, go outside of the picture, and in this case, this part which goes outside of the picture, it should be assigned 0 weight, whereas you just, from that area, you would predict from another picture only. The difference based is like you average samples which are similar in both pictures, and samples that are different in 2 reference pictures, you would use one of them with a higher weight. A wedge compound mode, yet another one. In this case, you can split the block with basically with a linear boundary into 2 parts, and you basically take one part from one frame and the other one from another frame, and there is a blending function in between, and AV1 uses the linear blending function, AV2 uses a sigmoid, and also you can use different width of the blending boundary depending on the block size. Also, you have more different subdivisions, so more wedges to choose from. A very interesting tool and very useful, actually. It brings a lot of gains. It's a temporal interpolated prediction. So what you do is you use the motion information, like the same that is used in the temporal motion vector prediction. You use it to actually interpolate a frame between two frames, and you use this frame for prediction. So there are two ways how you can use it. One is at the frame level, you can actually directly output the interpolated frame without adding any more information, and that's actually, you just do the loop filtering and you output it. And that's pretty good for very low bit rates. For the higher bit rates, you would usually use this frame as a predictor, and on the block by block basis, you can take this a block from this frame and use for prediction. And a good thing is that you use just one motion vector, but in fact, it's like by prediction because the frame was already interpolated from two frames. Some other tools, actually the next two tools, they're somewhat similar to each other. You get the by prediction with motion vectors, and you try to refine this motion vector in the decoder. So one way to do it is to use the optical flow refinement, and that's the OPFL tool. Also can be used for the TAP temporal interpolated frames that I just mentioned at the previous slide. Another way how you can do it is you basically have a 5x5 neighborhood close to a motion vector, and then you just start trying different like combinations of these motion vectors, and you pick in the decoder, you pick the one that has the lowest difference between these two prediction, which kind of indicates that that's probably the true motion vector. Yet another mode is warp prediction. So, and that mode captures the non-translational motion, and it uses a fine model with up to 6 parameters. So the translational and 4 more parameters to produce the fine mode. We have like 4 different warp modes. And they differ in what information you signal and what information you can derive from the neighborhood. So there is a difference from AV1, for example. In AV1, the warp mode used to implement the affine transformation. It was implemented as 2 shears, but that kind of, it limited the amount of warping that you could use. And now in AV2, you split into 4x4 blocks, and then you do each you find the parameters for each block independently and you combine them. Of course, you do the loop filtering after that, deblocking, and that allows you to actually use more warp than in AV1. Yet another tool is a block adaptive weighted prediction, which is basically illumination compensation. So you use the prediction with a function of AX plus B. So you have a scale and an offset, and there is also a possibility to derive, for example, some of these parameters from the neighborhood. So in this way, again, they're implicit and they are not signaled in the bit stream. To predict the motion vectors, typically you would use the spatial neighbors, so the temporal neighbors. You use the dynamic reference list, and that's the list of the possible motion vectors that you could use. Of course, you can signal the vector difference on top of that in some cases. And we also introduced the warp reference list, and that list basically takes into consideration the warp models, and that's for the affine motion model. A good, interesting tool is the reference MV bank and the warp parameters bank, and that means that you can actually save some of the motion vectors and warp parameters in the memory, and you can reuse even if you don't have them as the neighbor to your current block. So that helps if, for example, you used some motion vectors previously, then the motion changed, and then you want to use the same motion vectors again. The motion trajectory tracking has been improved. So basically, you can support the nonlinear motion. So and these models, the mapping table is stored in the video codec in the memory, and that improves the TMVP and SMVP. Very quickly, motion vectors could be signaled at different resolutions. For example, the different granularity may be introduced depending on the motion vector size, or sometimes it can be explicitly signaled. The coding of motion vectors, they are not coded as two different X and Y components, but you code the shell, so-called shell, which is like a sum of absolute values from these two components, and then one of them. And the range of motion vectors has been increased. Transforms, still 16 primary transform types, basically four types for the horizontal and 4 types for vertical. DCT, ADST, flipped ADST, and identity, so basically no transform. AV2 has some improvements on the transforms, so now the butterflies were replaced primarily by the matrix multiplications. We have some learned unitary transforms. For the large transforms, which are 64 by 64, you can actually generate the 32 by 32 residual and then upscale it. And that's how it's used. Usually, that's a pretty low pass parts of the picture, so it works. There are secondary transforms which are applied to the lower frequency coefficients, and they are basically learned transforms based on the data, non-separable. And finally, there are cross-component transforms where you can additionally decorrelate the two chroma coefficients. Quantization and entropy coding. There is scalar quantization as in AV1, and there was trellis-coded quantization was added as well as the parity hiding. So first of all, quantization. In AV1, quantization had like some kind of a custom table where you can see these curves like with shape, and that's basically the Q index versus the logarithmic quantization step. So in AV1, in AV2, that was replaced with exactly the exponential function. So you can see it as like the green line, and basically every 24 steps you have you are doubling the quantization step. Also now all of the different tables are the offsets from these exponential functions, and you have 256 levels for 8-bit content, 304 quantization levels for 10-bit content. And the range was actually expanded because in AV1, the quantizer, the highest quantization was not as strong as, for example, in HVC or VVC. Now it's about the same as in VVC. So you can go lower in the bit rate. Quantization matrices have been improved. They are now cheaper to signal, and you can have the user-defined quantization matrices, and different parts of the pictures could use different quantization matrices. Well, trellis-coded quantization is basically two overlap quantizers, and you can switch between them depending on the parity of the previously encoded coefficient, which improves basically the quantization. Parity hiding has similar approach, but just for the DC coefficient. Coefficient coding has changed, so you have, for example, typically you would assume that your lower frequency coefficients are the most significant, which corresponds to the top left corner. But if you don't apply transform, like for example, if you have this identity transforms, then sometimes due to Intra prediction, it's actually the opposite. So your bottom right corner has more significant coefficients, and for that you use a reverse scan in the forward skip coding tool, which helps in, for example, a lot in the screen content. The entropy coding, there are some improvements in adaptation rate adjustment and some simplifications. For example, the arithmetic coding engine in AV1 could have symbols up to 16. Now it's up to 8. And there are some further improvements, including the probability initialization, where you have basically in AV1 you just inherit it from one frame. In AV2 you could average from 2 different frames, or in case of tiles, average them across tiles. In-loop filters, and that's close to the end of my presentation. So 5 in-loop filters. The CDEF is the same as in AV1, and then there is deblocking, 2 filters in parallel, CCS on, CDEF, and then improved loop restoration and guided detail filter. So the deblocking has changed significantly. Basically, multiple filters are replaced with a generalized formula, which for the same formula for multiple filter lengths. And also it increases slightly the length of the maximum length of the filter. You can see that the difference is like you have some, in the picture, you have the blue signal is before the deblocking and red after the deblocking, and there is some texture on the 2 sides and it doesn't disappear, which helps you can apply the deblocking more aggressively due to that in the RDO process. And here is, for example, the result. I don't know if you can see it, but for example, from here you can see that the AV1 deblocking shows some block artifacts. AV2 deblocking doesn't have them, and it also brings about a % bit rate savings. Cross-component sample offsets, you basically try to improve luma and chroma from the luma components. So first you extract the features, and based on these features, you retrieve the offset and you apply it. You basically have 2 ways of doing this. One based on the band, that means on the sample value, and the other one, in addition to that, you also add the gradients for the sample, and you improve your signal. The loop restoration is basically a Wiener filter with or without classification. We have 3 different types there, and here you can see the coefficients that can be sent explicitly signaled and applied to the restoration units. So basically the picture is split into the restoration units. Also, you can do the loop restoration with with fixed filters that you could see here. In this case, you do it based on the classification. So for a 4x4 block, you find gradients, and you take some other information, and based on that, you pick your filter. Guided detail filter, a new tool from Samsung. It's basically it extracts features, vertical feature, horizontal feature, and then the mix feature, and based on that, again, it converts it to the table index, it extracts some offset, and it applies it to the output picture. And I'm almost done. So some features in AV2 are for some particular use cases. For example, screen content coding, you have a palette mode, you have intra-block copy. And one important improvement with the intra-block copy in AV2 is that now you can use intra-block copy and the in-loop filters, because in AV1, if you're using intra-block copy, you couldn't apply the in-loop filters due to some implementation constraints. Now you have 2 modes for intra-block copy, and you can apply the in-loop filtering on top of that, which improves quality on the screen content. Another important aspect is multi-layer and multi-stream video. For example, here you see that you can send 4 different streams, and then you combine them based on the information sent in the Atlas OBU. So for example, you can have a background stream, and then some of the parts of the video overlapped on top of that. Also supports the stereo video. Again, enhancement in the multi-layered coding design. You can now have more reference frames if your decoder level allows, and scalability is improved in general. As Li-Heng mentioned in his talk, still AV2 has film grain, which is a mandatory tool. There are some changes that we have done in the film grain design. In particular, you can now choose between larger and smaller block sizes, and some improvements in the signaling, and also in the randomness of the offsets. So the conclusions. Basically, the development of coding tools in AV2 is almost complete after almost 5 years of the development. Basically, the low-level tools have been finalized by now, and there are a few pending items related to the high-level syntax design, and the specification writing is also ongoing. So the final AV2 release is planned by the end of this year. Basically, the status is that we currently get the PSNR YOV gains in bit rate of 28.6% and 32.6% in VMAF bit rate. And we are working on the AV2 verification tests. So the future work includes optimization for the decoder and decoder software speed. That's one thing that we want to improve. Also, the encoder side improvements and encoder tools for like visual quality optimizations. And of course, future AV2 extensions after we finalize this. Profiles, perhaps some profiles including higher bit depth or maybe something in the AI or ML extension area. Thank you for listening.